In this video, I'm going to go over the Chapter 21 practice problems. Number 1. The force on a charged particle created by its motion in a magnetic field is maximum at what angle between the particle velocity and field? So the answer is 90 degrees, but the reason you know that is because if you have some external field going one way, then this is the field here. The charge, if it's moving parallel, if the charge were moving this way, it would not experience any force. The angle between the velocity and the field here, the angle would be 0. The equation that gives us the force, QVB sine theta, if you put in 0 degrees here, sine of 0 is 0, you get force equals 0, right? But if you have the magnetic field one way and then the charge is moving perpendicular, then now the angle between them here is 90 degrees. Sine of 90 is 1, so 1 is the maximum value that the sine function can have. So the force will be QVB. That's the maximum value that it can have. Any angle in between 0 and 90 will give you a smaller force. Number 2. In a mass spectrometer, an ion will have a smaller radius for its circular path if... So the mass spectrometer is that machine that we talked about where you have some magnetic field, some external field, and then you have some ions that are shot into that field. Let's say from over here. There's some potential difference here, down here, that gives them energy and shoots them up, these charges. But now that they're moving in this external field, they're going to experience some forces. And because they're moving perpendicular to that field, that force will cause them to move in a circle. That force is a centripetal force. It's always perpendicular to the motion, and so it'll cause it to go in a circle. And depending on the mass of the ion that's being shot up here, the circle that it will make will have different sizes. So we want to know, how do you get a circle with a smaller radius? So these ions will be separated according to mass. Some of them will land here, some of them will land here. So the equation that we derived for this case came from setting the magnetic force that the charge experiences equal to centripetal force. We said QVB was equal to mv squared over r. And when we solved this equation for r, we got mv over qb. So we're saying that this magnetic force that the charge feels makes it go in a circle. The radius of that circle will be given by this. So the smaller radius is going to be for a greater charge, right? If you make q big here, then r will be smaller. If you made speed bigger for part A here, then r will be bigger. If you made m bigger, r will be bigger. If you made b smaller, r would be bigger. So making q bigger is the only choice out of these that will make the r smaller. Typically in the spectrometer, the charge of the ions might be the same, but just the mass would be different. And so by keeping Q and B and V constant, you can sort them according to their mass. Number 3. Two parallel conductors are carrying currents in the same direction, so in class I drew them up, so I'll just draw the two currents going this way, same direction. And they're not necessarily the same currents, and the magnitude of the field between them is 40. So we got a field here. We don't know which way it is, but it's either into or out of the page. But we have a number, so I'm not going to do a dot because that might make you think that the field is coming out of the page. So the field right here, somewhere midway between them, is this value. If one of the current then has a direction reversed, what's the resulting field between them? So now you're going to flip one of the currents. So this is a conceptual question that you don't have any numbers, so it's about, do you understand which way that the fields are going? And do the fields add up in the center, or do they cancel each other out? Now, because the currents are not necessarily equal, the fields will not completely cancel out. In the example we did in class, the fields completely canceled out. In this case, if you're looking at the first case here, the field due to this wire, if you use the right hand rule, curl your fingers, the thumb points to the right, you'll have your fingers coming out of the page above the wire, and the fingers going into the page. I drew that incorrectly here. The fingers coming out of the page here and into the page here. So anywhere below this wire, the field due to that top wire is going into the page. And then for the bottom wire, the current's going in the same direction. Anywhere above this wire, the field is going to come out of the page. Anywhere below the wire, the field is going to go into the page, just like for the top wire. But now if you're looking at this region in between the wires, you've got one field going into the page, and I drew it up here, but I could have drawn it in the center. The field due to wire 1 is going into the page. The field due to wire 2 is going out of the page. So that means that they're partly canceling each other out. When they partly cancel each other out, the resulting field is 40. If you want, you can consider that any field going into the page, let's say, is positive. I'm just arbitrarily choosing a positive and negative so you can see this differently. So that means B1 would be positive. And then when you're adding B2, but since B2 is in the opposite direction, we'll call out of the page negative. That means you get B1 minus B2 equals 40. Since the fields are not the same because the currents are not the same, then it doesn't equal 0. Now over here, you're changing the direction of the wire. So the field due to the top wire, wire 1 here, when your thumb points to the left, your fingers are going to be coming out of the page due to wire 1 here. And I shouldn't be drawing a circle because we said we just draw the circle for the current. So I'll just draw the dot and the X here. So out of the page. Now for wire 2, we already discussed that if you're above wire 2, your fingers are also coming out of the page in between the two wires. So that means that the fields are going to be reinforcing each other. They're in the same direction. So I could say negative B1 minus B2, but we just care about the strength of the field. So we're going to say the strength of the field is going to be due to both of them added together because they're in the same direction. So when you subtracted two numbers, it gave you 40. Well, when you add them, you must get something greater than 40. Right? For example, let's say you had 60 minus 20 to give you 40. Well, now if you add 60 plus 20, you're going to get 80. So that's one way, just to make sure the positives and negatives didn't confuse you. If we want over here, we can say that a field that is going out of the page is positive, and we can say negative B1 plus B2. That way we can keep the fields positive here. But you can pick if going into the page or out of the page, which one is positive and negative. That doesn't matter. What's really important is simply that if they are going in opposite directions, that you subtract them. If they're going the same direction, that they're adding together.